I cannot believe I've made it through 24 lectures and actually remembered to press the button, but I've got this little sticker that I had on my computer to remind me. Yeah, not my strongest trait, remembering things like that. Anyway, this is the last lecture. We officially have a lecture slot next Tuesday, but this seems like a reasonable place to end the material, and I think we've worked pretty hard this term. It seems reasonable to take one final lecture off. I will have lecture or office hours as normal next Tuesday if you've got any last questions on the assignment. I also have office hours today, 4 to 5. And I was going to say I will post office hours through the exam period as you prepare for the exam, but I guess that'll only be for a smaller group of students. But anyway, I'll have some times available for you if you wanna talk. Okay, we've got one last topic to look at in reaction diffusion systems, and it's a kind of an interesting one. Okay, I think it's interesting. I think all of this stuff is interesting, of course. It's about Turing instability and pattern formation. I think when I talked about these instabilities, I think I may have attributed the whole thing to von Neumann. He did do some things in this pattern formation game, but the particular thing that I'm going to talk about is known as Turing instability. Okay, so let me turn over to other Brian, and I will move out of full screen so I can see the Slack channel in case I missed some questions coming. This is a small group, a small elite group, and so I think at this stage, you can just turn off your microphone and ask your questions if you want. If you're happier putting them in chat, that's fine too. Okay, so last lecture. I mean, it's been fun, but okay, what can we say? I know you probably know. I won't be offended if you go, yeah, great, Math 400. I'm happy to see the end of that. I hope you learned something. So today we're going to talk about Turing instability. Which you can show with a vector example, okay? But I'm going to show you an example of how it works in reaction diffusion systems. And how it can lead to pattern formation. To be honest, the pattern formation in this 1D example that I'm going to show you is not so exciting. But if you look online, you can do reaction diffusion systems pattern formation, and you can see all kinds of funky 2D patterns that can come out of these kind of systems. I'm just going to talk about a 1D, one linearized, so you can see how the patterns form with a preferred length scale, and then I'll leave it to you to look at the pretty pictures online if you like. Okay, so Turing instability. This is a funny thing. Actually, I was wondering how to phrase this. Right, because you want to say there's a mathematical thing, right, that you can show, but it's not a theorem because it's basically saying, hey, this thing that you expect should happen doesn't always happen. So I don't know what you would call that. I'm going to call it the Turing observation. Okay, and that is, I'm going to have a system. I'm going to write it as a vector. We're going to have actually a vector of continuum functions. So I'm going to have a u of x and t and a v of x and t, but you can just think of them as vectors now, right? And they're going to have, I'm going to have two systems, right? Two dynamical systems, so two ODEs, where they have a shared stable equilibrium. And of course, if there's an equilibrium anywhere, you can just shift it so that mathematically it's at the origin. So this is going to be a stable. And I don't know if any of you heard about these different sort of ideas or took Math 345, but I'm going to say it's an asymptotically stable equilibrium. There's different ideas of stability. Asymptotic stability means that if you start near this equilibrium, then as t goes to infinity, you limit towards it, right? There's other kinds of weaker stability where you know, you could have oscillations that just don't get bigger as you kick it away from the equilibrium. So no, this is a stronger sense that, like, you start near this equilibrium point and you move towards it, right, as t goes to infinity. It's going to be an equilibrium of two dynamical systems. M1 and M2. Okay, so what do I mean by that? So what does this mean? This means if I'm looking at this, let's say it's an ODE, right? Right, it's autonomous, there's no t, right? Then if I have the limit as t goes to infinity of u of t, I get 0. And this is for all initial conditions in a neighborhood of 0. Right, so you have a little disk, at least around the origin, where if you start anywhere in that disk, you tend to the origin as t goes to infinity. There's another thing which is also a kind of a strong flavor for stability of equilibrium, which is that there's a neighborhood where you don't leave, right? Right, you start in that neighborhood, you don't leave, and you tend to the origin. Because there's some weird dynamical systems where you can have everything end up at the origin, but they take big loops like around in the phase space to be able to get back. So we've got as strong an idea of stability for this thing as you want. Okay, so let's put that into, but let's not write it down because it's too much writing for me, right? And I've also got the same thing for this other dynamical system. For all U0 in a neighborhood of the origin. So what's the observation? The observation is the origin is not necessarily stable for the system M1 plus M2, which is kind of interesting, right? So if I look at some the whole class of such M1 and M2, right? I'll say there are examples, right? Of course, there's a whole bunch of M1s and M2s where, yeah, you add them together, it's also stable. But there are examples where solutions of this thing all leave a neighborhood of a u equals 0 for all initial conditions well, not the exact origin because it's a fixed point, right? But for all initial conditions, not exactly at the equilibrium point in that neighborhood. Right, and if I wanted to draw a 2D picture, it would be, here's my neighborhood, and right, here's the origin. Right, so I exclude this thing because if I start on the origin, I know I just sit there, right, even though it's unstable, right? Any place I start with here, the solution has to leave. And so if you were going to draw sort of the phase plane thing, it would be all of the arrows would be pointing outwards from this neighborhood, right? Which is pretty interesting considering that the things that you used to put this together all have the property that the arrows are all pointed inwards, right? So how does that go? So again, you need at least two components. You can look and see that if it's a one component thing, that you can't get this instability. So you have to have at least two components, and you can find examples in reaction diffusion equations. Right, okay, so let's have a look. You need at least two components, so let's have a U and a V. Right, I'm gonna have diffusion. It turns out that it's essential that the diffusion constants can't be the same. They have to be different. And I've got some reaction terms. So this is going to be my M1. Like we know all about diffusion at this point, right? It just, right, as time goes to infinity, that just damps everything out, right? The solution goes to 0. And I'm going to give you some conditions for where we can talk about a stable equilibrium that includes those terms. Okay, so these are diffusion constants, or coefficients. They're both positive. Right, I got no funny business with backward heat equation coming on. So here's my equation 1. So now I'm going to suppose that the reaction has a stable equilibrium at concentrations U0 and V0. So here comes the M2 part, right? So it's an equilibrium. So now I know that when I look at the right-hand sides at those concentrations, I get 0, and I get 0 for the other one too. Right, okay, and I want it to be asymptotically stable. So I want this thing to have a negative exponential behavior towards that equilibrium. And you can look at that by looking at the Jacobian matrix of partial derivatives. Jacobian, okay, I got some extra letters going on there. this is df du, df dv, dg du, dg dv. I'm going to evaluate all of those coefficients at this equilibrium point. And then that's a matrix that's describing the linear behavior near the equilibrium point. And I want to have exponential decay. So this, I'm going to say, has two eigenvalues. And they both have negative real parts. And the 2x2 case is really nice, right? There's a pretty nice way to characterize when this J has that property. It's also going to be the thing that's going to let us analytically see how we can destabilize the stable equilibrium in certain cases when we pick the diffusion constants just right. And so I've got my lambda 1 and lambda 2. They've both got negative real parts. Of course, this is a real matrix. So even if they are complex conjugates, when I add them up, right, I'm going to get a real negative number. So this has to be less than 0. The other thing I know is if I've got the sum of the eigenvalues is equal to the trace of the matrix. Okay, that's something I know. That would be a pretty obscure fact from Math 221 or 152. You might have seen it in 307. Okay, it's a linear algebra fact, okay? The one you probably have seen, though, is that if you look at the product of the eigenvalues, that's the determinant. And if they're both real and negative, right, then if you multiply them together, you have to get a positive number, right? And if they're complex conjugates, right, then if you multiply them together, you get the absolute value squared. So either way, this has to be a positive number, right? So if you have these two things, right, the trace is less than 0 and the determinant is bigger than 0, then you've got two eigenvalues with negative real parts, whether they're real or complex. Well, okay, I don't like looking at everything around the equilibrium U0, V0, so I want to shift it so it's at the origin. So that's pretty easy to do. We're just going to shift, right? So note, we will consider, you know, what we were calling U, we're going to shift it by that amount. And okay, I don't want to call it something U, so I'm just going to relabel that as U again, right? And now I'm going to have the equilibrium at U equals 0. And then after that shift, we're going to linearize the equations, keeping only the Jacobian matrix. So we're looking at what's happening near the origin. As long as the eigenvalues aren't 0, that tells us the whole story. That's something, yeah. See, I haven't taught 215 or one of those courses. So I'm not exactly sure what they put in that course these days. I've taught the DE part of Mech 2, I guess, is the only thing I've taught here at UBC. Well, Ken, I can't remember whether we do that there either. But anyway, so you can linearize and you get, well, the diffusion term's already linear, so that doesn't change, right? And now you get this Jacobian matrix coefficients. Right now they're evaluated at the origin, but it's the same Jacobian matrix as before. Oh, and this is times U, and this is times V. And then I get, this is already linear, the diffusion term. And I get dg du times u plus dg dv times v. Right. And just to make sure we understand it, I can write this in vector form with u having these two components. It's really should be thought of as a column vector because I'm going to be doing some matrix multiplication. There's the time derivative of the u vector. There's this diagonal diffusion matrix. And then there's this Jacobian matrix times u. Right? So here's the M1 part and here's the M2 part. On their own, right, u goes to 0, right? So it's kind of interesting that we can put these two things together and get something that is actually unstable. Well, okay, so now we're back to Math400 techniques, right? Because this is a constant coefficient Cauchy problem. And so we're going to analyze it with the Fourier series. So we know we can analyze it with Fourier series. Now, it's going to be well posed, okay? It's going to be well posed. But now we're interested in not just whether it's well posed, but are there any positive exponential growth rates that you can get out of this, which seems sort of funny, right? Because here I'm going to have the minus alpha squared stuff going on. And then these guys, I've got the lambda 1 and the lambda 2, which are both negative. So it's okay. I think this is an interesting thing. Many other people have thought this is interesting too. You can put these two things together and get instability. I'm not sure if you're at this stage yet, but analyzing with Fourier series is the same as consider solutions of the form u of x and t. Well, I'm going to consider a Fourier component, right? And I want to know how that Fourier component depends on time, right? And I'm going to consider a constant vector that's like going to be an eigenvector. That's not an eigenvector of J, but an eigenvector of minus D1 alpha squared minus D2 alpha squared, that matrix plus J, right? Okay, so let's see how this game goes. Let's take this form and put it in here and see why it's the right thing to look at. Well, okay, so when I take the time derivative, I get lambda e to the lambda t, and then I get e to the I alpha x, and then I get this constant vector u. Right? When I take the second space derivative, I get the minus alpha squared coming down. So now I get the e to the lambda t, e to the I alpha x, but I get a vector which has got one component minus d1 alpha squared u and minus d2 alpha squared v. This is the vector that has components u and v, just a constant vector, right? And then I get plus e to the lambda t, e to the I alpha x, and then I get the j times u. right? Right, so now I can see e to the lambda t, that shows up everywhere. E to the I alpha x, that shows up everywhere. And I just get the eigenvalue problem, well, that I knew was going to come because I've done this before. And if you did Math400 a little bit longer, okay, but that sounds like a threat. Okay, so I'm not not threatening you. But if you had to do Math400 a little bit longer, this would be straightforward for you as well, right? You'd know, hey, this is what's going to happen. I just can put this in and see the eigenvalues of the matrix I know that will come out. And the matrix that you know will come out is this matrix J. There's the J. And then it's going to be minus, then this minus D1. Sorry, it's J. Okay, I got too many minus signs. Minus D1 alpha squared, 0, 0, D2 alpha squared, times this vector u is lambda times u. Right, so this is the rate of growth in time, right? The lambda is, there's going to be two of them, and they're going to come from the eigenanalysis of this particular matrix. Okay, so I can write that out. That's the Fu minus D1 alpha squared, Fv, Gu minus D2 alpha squared. So now I can say if the real part of lambda 1 or the real part of lambda 2 are positive, then the system is unstable. So I've started with two things that are stable. I've added them together, and now I'm checking to see if I can arrange things so that I can get an unstable behavior coming out of this thing. Okay, and you can. Turing was a smart guy, and he's got this thing named after him that many people have looked at. So, oh, there's a comment from Matt. Yeah, I got a typo. This is GB. Thanks. Okay, so let's have a look. So let's remind ourselves what we're looking for. So we are looking for a Turing instability example. Anyway, this is a matrix, but it depends on alpha. So the Turing instability example then should be, well, I should have A at 0. That's the original, this is the original J. This should have eigenvalues with negative real parts. Remember, we're trying to show, hey, there really are these examples that could come up in this particular setting of reaction diffusion systems, where you can start with two stable things, add them together, and have some instability come from it. Okay, so remember that means that the trace has to be less than 0. That's the sum of the diagonal entries. If trace is not a thing that you know, and the determinant has to be bigger than 0. And if we're looking for a Turing instability example, then I should be able to look at some other alphas. this should have at least one eigenvalue with positive real part. For some alpha. Okay, so let's just think about this. The trace has to be less than 0, right? Right, and the determinant has to be bigger than 0. Maybe this is something hard to do, you know, while listening, but hopefully this will be clear. If F, U, and GV are both negative, right? Okay, well, that gives me a trace less than 0, right? But if they're both negative and I subtract stuff, right, then the trace will stay less than 0, right? And I'm just multiplying two negative numbers together that are getting more and more negative. I'll just keep the determinant positive. So if F, U, and GV are both negative, you can't make it go unstable with alpha, right? So for this property, I'm going to need F, U, and GV to have opposite signs. Okay, and so if F, U, and GV have opposite signs, then as I'm working out the determinant, right, I'm going to have a negative number, right? And then I have to subtract the GU times FV, and I have to get something that's positive, right? And so now if I look at this condition at 0, then I'm going to need GU and FV. They also have to have opposite signs. This still isn't enough to guarantee Turing instability, but at least now I know the kind of thing that I'm looking for. Anyway, so then I played around in MATLAB, okay, all right, with these criteria, right? I played around, and I came up with the Jacobian matrix. Remember, this is this A at 0, right? And I came up with this one, 1, 1, minus 2.1, minus 2. Okay, and of course you can see the trace is negative and the determinant is positive. And just to check, I did the MATLAB thing where you get negative eigenvalues. So this passes the first test for the Turing instability. I'm adding two things together that are stable, right? So now I have to destabilize it though with some alpha going on, right? So now I picked some coefficients. This is a pretty typical scenario. Okay, so let's just think here for a minute. Let's look at what this means, right? This means I got U dot is U plus V. This is the linearized reaction, right? U can go negative because remember, this is a deviation from equilibrium. So I could go below equilibrium and that makes this U negative. So we're not talking about negative concentrations, right? Because that doesn't make sense. And then I get a V dot is minus 2.1 U minus 2V, right? So U wants to grow, right? U would left on its own, right? I'd have U dot is U, right? I'd have exponential growth, right? but growing U, right, decreases V, right? And as you decrease V, then you decrease U, right? So that's what stabilizes this whole thing, right? Is the feedback between U and V. Remember I said you needed two components to do this, and you can't do it with a diagonal system either, right? You got to have this interplay between the two components to get this kind of instability to happen. So I'm picking this diffusion for the second component to be big, okay? Now I'll show you an alpha and we'll see a positive number, right? But the sort of physical or chemical, I don't know how much chemistry you guys are into. For me, it's small amount, right? But this diffusion being big, this is what is actually going to lead to the instability, right? Because let's look at this cycle again, right? U wants to grow, right? But then the growth in U makes V decrease, and the decrease in V limits the growth in U, and it's stable, right? That's without diffusion, right? Now, I add this big diffusion in, and what happens is U wants to grow, right? But then it starts to decrease V, right? But then V diffuses away quite quickly, right? So that decrease in V is spread out, right? And then this thing can locally, it has enough ability to grow that it can overcome the negative feedback from V. Anyway, I can just show you the numbers. I'm going to pick a wave number 2, right? I'm going to get A at wave number 2, right? That's, well, 1 minus alpha squared times D1. So 1 minus 0.1 times 2 squared. I get the 1, I get the minus 2.1, those don't change. And I get the minus 2 times 2 squared, right? That's 0.6, 1 minus 2.1 minus 10, right? And you can see now that the trace is negative, but the determinant is also negative, okay? So now you can see that things have not remained stable. So I've got lambda 1, I've got a big negative eigenvalue, but I've also got a positive eigenvalue. Right, so this is unstable. Okay, now let's just have a look, all right? I'm gonna go in alpha. I'm gonna look at the maximum of lambda 1 and lambda 2, right? When I'm at 0, I'm stable, right? I know at 2, I'm unstable, right? If you look at this thing, right, as alpha goes to infinity, eventually this term goes negative, right? And once this term goes negative, then the trace is going to be negative. It's always negative, right? The trace will be negative, but once this goes negative, the determinant goes positive, right? So you know somewhere out here, past here, everything is stable again, right? So the shape of this thing looks something like this. You can work out what this maximum alpha is if you care, right? It's when the determinant is, oh, there you go. It's when the determinant is 0. You can work out the alpha for when the determinant is 0. And that'll be this case as well. So if you think about this, right, this is a window of unstable modes. Right? So you don't get instability just like uniformly. It's not uniformly growing, right? Exponentially. There is a maximum, right? A maximum growth rate. That's the one that's growing exponentially the fastest. So if you start with any kind of little wiggles, right, on the equilibrium, eventually you're going to see solutions that are more or less, right? This is a pattern with alpha equal to that maximum value, the wave number equal to that maximum value. This is the thing that's growing exponentially. So the two interesting things that come from this. So, okay, an example of Turing instability, right? It's kind of an interesting, unintuitive result that in these vector cases, you can destabilize things even though you're adding together to stable dynamical systems. You can get something that's unstable. The other thing is, if you think that you can tune the chemical parameters and the diffusivity of the chemicals, you can get patterns growing with any spatial pattern that you want, right? So remember, this is for the linear version of the problem. And so if you put the nonlinear terms back in, then you can get patterns that saturate at a certain amplitude. Think of the logistic equation. Right, the logistic equation, you know, had exponential growth near 0, but then it like limits out and at an amplitude of 1. So if you put, you know, realistic reaction terms in, you will get patterns form. They will at least start forming at a particular wave number, right? And then they'll saturate out. So the pictures you see online are often steady state or near steady state results of these kind of reaction diffusion problems with instabilities from this Turing mechanism. Okay, that's all I had for today. The last lecture, and it's short. I'm a great guy today. Let me let me stop recording, but then I'm happy, as always, to take any questions from the audience in a sort of informal office hour setting if you've got any now. And otherwise, I'll be back 4 to 5 today.